Hello, my name is Tejesh Acharya. My roll number is 20951A04M0. I'm from ECD section, and my topic is relate set theory and probability theory. So, coming to the relate set theory and probability theory uses the language of sets. As we will see later, probability is defined and calculated for sets. Thus, here we briefly review some basic concepts from set theory that are used in this book. We discuss set notations, definitions, and operations such as intersections and unions. We then introduce countable and uncountable sets. Finally, we briefly discuss functions. This section may seem somewhat theoretical and thus less interesting than the rest of the book, but it lays the foundation for what it is to come. A set is a collection of some elements. We often use capital letters to denote a set. To define a set, we can simply list all the elements in curly brackets. For example, to define a set AA that consists of the two elements, we write A equals and A equals. To say that belongs to A, we write belongs to A and it belongs to A, where is pronounced belongs to. To say that an element does not belong to a set, we use does not belong to. We may write heart does not belong to A, heart does not belong to A. Set theory is a branch of mathematical logic that studies sets, which can be informally described as collection of objects. Although objects of any kind can be collected into a set, set theory as a branch of mathematics is mostly concerned with those that are relevant to mathematics as a whole. The modern study of set theory was initiated by the German mathematicians Richard Dedekind and George Cantor in the 1870s. In particular, George Cantor is commonly considered the founder of set theory. The non-formalized systems investigated during this early stage go under the name of naive set theory. After the discovery of paradoxes within naive set theory, such as Russell's paradox, Cantor's paradox, and Bureli-Forti paradox, various axiomatic systems were proposed in the early 20th century, of which Zermelo-Fraenkel set theory, with or without the axiom of choice, is still the best known and the most studied. Set theory is commonly employed as foundational system for the whole of mathematics, particularly in the form of Zermelo-Fraenkel set theory with the axiom of choice. Besides its foundational role, set theory also provides the framework to develop a mathematical theory of infinity and has various applications in computer science, such as in the theory of relational algebra, philosophy, and formal semantics. Its foundational appeal, together with its paradoxes, its implications for the concept of infinity, and its multiple applications, have made set theory an area of major interest for logicians and philosophers of mathematics. Contemporary research into set theory covers a vast array of topics, ranging from the structure of the real number line to the study of the consistency of large cardinals. Many mathematical concepts can be defined precisely using only set theoretic concepts. For example, mathematical structures as diverse as graphs, manifolds, rings, vector spaces, and relational algebras can all be defined as sets satisfying various axiomatic properties. Equivalence and order relations are ubiquitous in mathematics, and the theory of mathematical relations can be described in set theory. Set theory is also a promising foundational system for much of mathematics. Since the publication of the first volume of Principia Mathematica, it has been claimed that most or even all mathematical theorems can be derived using an aptly designed set of axioms for set theory, augmented with many definitions using first or second order logic. For example, properties of the natural and real numbers can be derived within set theory, as each number system can be identified with a set of equivalence classes under a suitable equivalence relation whose field is some infinite set. Set theory as a foundation for mathematical analysis, topology, abstract algebra, and discrete mathematics is likewise uncontroversial. Mathematicians accept, in principle, that theorems in these areas can be derived from the relevant definitions and the axioms of set theory. However, it remains that few full derivations of complex mathematical theorems from set theory have been formally verified. Since such formal derivations are often much longer than the natural language proofs, mathematicians commonly present one verification project, MetaMath, includes human written computer verified derivations of more than 12,000 theorems starting from ZFC set theory, first order logic and propositional logic. Citation here. So this is the drawing, and you have the difference between experimental probability versus theoretical probability. Experimental probability is found by repeating an experiment and observing the outcomes. P event equals number of times event occurs divided by the total number of trials. For example, a coin is tossed 10 times, head is recorded 7 times and tail 3 times. So P by head equals 7, that is the number of times the head occurred divided by the total number of trials the experiment had, 7 by 10, and the same for P tail, 3 tails and you have 3 by 10. Theoretical probability is what is expected to happen based on mathematics. So the formula for it is number of favorable outcomes, total number of possible outcomes. So it's assuming what's going to happen by conducting that event. It's the theoretical part of it. So coin is tossed. Let's assume there are two whole outcomes, either a head or a tail. So 2 is the total number of outcomes, and there can be head ones or a tail ones. So if it's head, it's 1 by 2. If it's tail, it's another 1 by 2. So that's a theoretical probability. So we saw about probability theory, we saw about set theory, and we saw its applications and the types it has and what kind of foundation it gave for various subjects, not just mathematics but even for philosophy, philosophers, logicians, etc., and how it deals with paradoxes, etc. And we saw the difference of experimental probability versus theoretical probability. Thank you.